Okay, here I am back to continue with the practice test 2 solutions. So first of all, I just want to point out that I did not have the final answer for T on the last video. So the final answer, or excuse me, for 7C is 4.16 milliseconds. Now problem 8. So if we look at problem 8, we have a combination of capacitors. Remember, capacitors in parallel add directly, whereas capacitors in series add inversely. So here we have C1 and C2, they're in parallel. So the equivalent capacitance for that is going to be C1 plus C2. And then for these two, C3 and C4, you just add those capacitance. So if we were to do that, we have C1 plus C2 is equal to the 1.5 farads plus 3.5 farads, which we get 5. And then C3 plus C4, 4.2 plus 5.8 farads, which is equal to 10. So we have those two, and then we're going to add those inversely. These were the parallel circuits, or parallel capacitors. And so now we're going to add the ones in series. And so here we have 1 over C equivalent is going to be equal to 1 over 5 plus 1 over 10, which is equal to 0.2 plus 0.1. So we have C equivalent is equal to 3.33 farads. Oops. Question 9 was a challenge problem for last semester. So I said this before in class, it's not one that I would put on this exam. It was the stretch, the one that I did to challenge people. It is would not be on our exam, but it's good to understand how this works. So this is an Ampere's law problem. And remember, Ampere's law tells you that if you sum the magnetic field along a little segment of a loop, and you add up all these contributions around a loop, then that's going to be equal to mu naught times the current enclosed within a loop. So the first thing is to choose a loop. We're asked to find the magnetic field at R. So I'm going to choose a loop that is at the radius that I'm interested in. And I'll draw that right there. And it's really meant to be a circle, radius R. And so since B is constant across this loop here, then I can say that this whole side is equal to the sum of all the little segments. So it's really the circumference of the circle times the magnetic field, and that's equal to mu naught. Now what's the current enclosed? Well, it tells me that I've got a current that's moving out of the center. So enclosed inside this purple loop or circle, I have I, but I also have a piece of the current here that's going into the page. And it's only a fraction of the total current being carried in this outer sheath. So I have to, because it's going the opposite direction, I take the current I that's from the center part minus I, but I've got to subtract amount proportional to the areas. So the area of this little ring is going to be equal to pi, the area of the outer circumference minus the inner. So it's going to be pi r squared minus pi r2 squared, and it's going to be divided by the total area of this outside sheath, which is pi r3 squared minus pi r 2 squared. And we can do some simplifications right here because there are some things that cancel. Some pi's cancel out. We can factor out I. And if we do all that, then we could solve for b. b equals mu naught I over 2 pi r. But I have this ratio of areas. So I minus r squared minus r2 squared over r3 squared minus r2 squared. And this actually can be simplified even more on this side. But I'm just going to leave it at that for that one. Notice that if we were in the case where r was equal to r2, then you would have just the result mu naught I over 2 pi r, which is just for the current carrying wire, which is what we expect. Part B is something I would expect you to know and could actually be on the exam. And in that case, it's asking for the magnetic field outside the cable. So what we would do then is we would put an ampere loop around the outside. And so this loop would have a radius r. So then, again, using Ampere's law, we would have the left side would become 2 pi rb, and that's going to be equal to mu naught times I enclosed. Well, I enclosed is we have I coming out towards us, but then we have I going in. Well, that's just 0. So in this case, B is equal to 0. Question 10 is one of the longer questions. So we have a capacitor in a circuit. It's kind of an RC circuit, but a little unfamiliar from what we've done in the past. And we're asked to find various variables in the circuit. So let's take a look at this. First of all, it says to label all the currents in the circuit. So I'm going to label those. And this is important because this tells you what direction everything is. It also tells me what you mean when you say I1 or what you might mean when you say I2. So make sure that you label all the currents. Then it says ask for Kirchhoff's loop law for the circuit that contains, and this really should be the loop that contains the EMF R2 and C. So if I look at EMF R2 and C, then my loop is actually this loop here. Call that loop A. So loop A is that we have, as I go around that loop, oh, and it's good to include the potential increases and drops. So as the current goes through here, it's going to go from plus to minus through this resistor and plus to minus. Charge is going to build up on the capacitor, and there's going to be a deficit on that side, and this one is automatically, the EMF is minus and plus. So as I go around loop A, then I'll find that we have an increase of potential at the EMF, and then I go through R2, and the voltage drops by I2 R2, and then it drops by the charge on the capacitor over C, and that's all equal to 0. So I have some numbers. Always put in numbers if you can. So it would be 12 minus R2 is 4, so 4I2 minus Q over, and C is 5, is equal to 0. We now have, after a long time, it asks what is the voltage. So we could look at, we don't have an equation that we solved for this, but we can look at this equation that we just drew and figure out what's happening. So after a long time, we know eventually the capacitor is going to be full of charge, and pretty soon it won't be able to take any more charge. It gets crowded. So after a long time, the current I2 is going to approach zero. It's going to shrink down to zero because it basically charge can't flow anymore. It's like crowded over on this positive plate of the capacitor. So if I look at my equation for loop A, I2 being 0, then that tells me that I have 12 minus 4I2, and I2 is going to 0, minus Q over 5, and this is really the capacitance on the, or the voltage on the capacitor equals 0. So if I solve this equation, I see that the voltage on the capacitor is actually 12. Now let's take a look at the next loop law. It says write Kirchhoff's loop law for a circuit that contains R1 and E. So R1 and E, this would be the loop that is right here. So we'll call it loop B. So loop B, if I look at that, I have an increase in the EMF. And then as I go through R2, the potential, or excuse me, R1, the potential drops. It's equal to 0. So if I put in the numbers, then I get 12 minus 2I1 is equal to 0. Then it asks what is the current through R1. Well, that means I just have to solve this. So that means that I have 12 minus 2I1 equals 0, and 12 is equal to 2I1, and I1 is equal to 6 amps. Okay. So in the next video, I will do question 11.